Okay, everyone, so we are back. As always, this is Dr. Jackson, and we are back for part three. This is the last section of the lecture for chapter six. Okay, so the sampling distribution, that's what we're going to talk about now. Remember, I briefly mentioned this at the very beginning of this particular lecture. So now I'm going to talk about it in more detail. Basically, what the sampling distribution does is it allows us to link information from the sample to the population. And it's considered the central concept in inferential statistics, all right? So also in your textbook, Healy, the author of the textbook, describes the sampling distribution, or the way that he defines it is as the distribution of a statistic for all possible sample outcomes of a certain size. And if you want to see that, just look at page 157 of the hard copy of the textbook. If you have a PDF version, I'm not exactly sure what page that's on, but that's in that glossary. That's where I'm pulling that from. So as defined in the glossary, this is how it's defined. The distribution of a statistic for all possible sample outcomes of a certain size. Under conditions specified in two theorems, which I'll talk about in a moment, the sampling distribution will be normal in shape, with a mean equal to the population value and a standard deviation equal to the population standard deviation divided by the square root of n. You'll see this on additional slides, but I wanted to just make sure I gave you that full definition of sampling distribution. Okay, so let's see. All right, so what this particular slide coincides with, it's the three distributions used in inferential statistics. And this is on page 150 of your course textbook. Yeah, so page 150 of the course textbook. And it kind of goes into detail about the three distributions, okay? The population distribution, the sampling distribution, and then the sample distribution. All right, so those are the three distributions that we have. And again, this is on page 150 of your textbook. So if you want to take a look at it in more detail, that's where you'll find it. You'll also find within the text itself, that's where you'll find the discussion and description of sampling distribution. So go ahead and make sure you read that expanded section that describes each one of those different distributions. What I have here is just a summary. Excuse me, it's just a summary. But basically, when it comes to inferential statistics, it involves these three different distributions. Information, like it says here at the very bottom of the screen, information from the sample is linked to the population by way of the sampling distribution, okay? So as you can see in that graphic, the figure 6.1, where it's giving you that relationship amongst those three distributions, you see that the sampling distribution is in the middle. And that's what links the population distribution to the sample distribution, okay? Because that sampling distribution, as was mentioned in the definition, the sampling distribution, again, it's a statistic for all possible outcomes of a certain size. And the conditions specified in the two theorems that I'm going to talk about, that's what helps it get to a normal shape. And so that's part of what helps link those two. It links the population distribution to the sample distribution, but that linkage is through this, the population, okay, the population is linked to, the population distribution is linked to the sample distribution, and it's done through the sampling distribution. My apologies, I just wanted to make sure I said that correctly and didn't say sample distribution twice. Okay, so moving on, a little more information. This particular example also appears in your textbook on pages 150 through 151. And it's just basically kind of giving you what it means, or kind of talking about, kind of giving you steps of the sampling distribution. So, like it says here, they want to gather information on the age of a community of 10,000 individuals. Well, they're not going to go out and sample all 10,000 individuals. That's a lot. But maybe what they do is they get the first sample of 100 people, then they get another sample of 100 people, so on and so forth. But in the first sample of 100 people, they get that sample, they get the information, they find out that the mean age is 27. Okay, great. Then they go and they get a second sample of 100 people. They find out that that sample's mean age is 30. And they continue, continue, and continue, and continue. That is essentially what a sampling distribution is. All right, so when they said they plot those ages on the, when they plot those ages, this is what they were talking about. So as you can see in the slide, they have sample 1 where it's at 27. So you have 26, sample 1, and then you have 28. So that's obviously 27. And then they plotted sample 2 on 30. And they would just keep doing that, okay? And the notion and the idea behind the sampling distribution is you do that and you continue to do that until you've exhausted every possible combination of 100 people. Now, obviously, we as researchers are not going to do that by hand, but this is the concept and the idea behind this, okay? Okay, so each sample, though, is unique. So there will be variation in the sample means. Now, if the EPSEM, equal probability of selection method, is followed closely, even if that method is followed closely, not all of the samples will be representative. However, the sample means that are near the population mean are common, whereas sample means that are far away are rare. So the sampling distribution is approximately normal. As with all normal curves, the distribution is symmetrical. So cases close to the mean, say within 1 standard deviation away from the mean, so that could be 1 standard deviation above, 1 standard deviation below the mean. Those are going to be the common cases. And cases far away from the mean, say beyond 3 standard deviations, those cases are going to be rare, okay? So when you have a sampling distribution, more of your cases typically are going to be closer to the mean, and that's what makes it like a normal curve, okay? And so that's what makes the sampling distribution approximately normal. We look at it and we think about it in terms of a normal curve, okay? All right, so this is actually the first theorem of the 2 theorems that I was talking about. So the sampling distribution, it's based on 2 theorems, and that's part of what helps make the normal curve, the sampling distribution approximately normal. So the first theorem, this is what you see here on the screen. It basically states it states, if repeated random samples of size n are drawn from a normal population with a population mean and a standard deviation mean, a population standard deviation, then the sampling distribution of the sample will be normal with a population mean and a standard deviation of the population standard deviation divided by the square root of the number, okay? And that population standard deviation divided by the square root of the number, that's your standard error of mean, okay? If you translate this, and your book does this in case when you're not looking at the lecture and you're trying to remember, okay, I don't remember how she put that in normal terms, you can always look at the textbook on page 152, and it's in the paragraph that appears right under the definition for this first theorem. So here's what this kind of means in normal speak, if you will. So basically, if you begin with a trait that is normally distributed across a population, they use IQ scores for the example. I'm actually going to move this to the next slide because this gives what I'm talking about. So you can see it on the screen, this in normal speak, if you will. So again, if we begin with a trait that is normally distributed across a population, for example, IQ, I also added height to the example. And then if you take an infinite number of equal sized random samples from that population, then the sampling distribution of sample means will be normal. Okay, so basically, if you start off with a trait that's typically normally distributed across the population, and you take an infinite number of random samples, equally sized random samples. So remember in the previous example, I think I said 100, when I was talking about age. And that example with age, I said you take a sample of 100 and you get a mean of 27. Then you take another sample of 100 and you get a mean of 30. Then let's say you take a third sample, you get a mean of 28. You take a fourth sample, you get a mean of 25. Okay. What ends up happening, because that population is normally distributed, whatever that trait is, it's normally distributed across that population. If you take a significant or an infinite number of random samples, then the sampling distribution will also be normal. Okay, that's what they're talking about here. So the key thing to remember with this first theorem is that this is what allows the sampling distribution, or this is how we can say the sampling distribution is approximately normal. And we can apply the concepts and aspects of the normal curve to a sampling distribution, okay? The second theorem, this is the central limit theorem, okay? This particular theorem, and I have the actual definition, if you will, as well as kind of like in lay terms, they're both on the same screen this time. But the definition that appears in the book, this is page 153 of the book. Oh, let me back up real quick. So let me back up 1 second. So this particular theorem requires that the variable be normally distributed in the population. Okay, that is a requisite. The variable has to be normally distributed in the population under the first theorem. With the central, wait a minute, stop, there we go. With the central limit theorem, that's not necessarily the case, okay? You know, we have to stop and think about not every single distribution and not every single formula is going to be normally distributed. So then what? Again, this is where the central limit theorem comes into play. And so basically what it says, and this is, oh, I am on the wrong slide, my apologies. So here's what it basically says, and this is what is on the slide. If repeated random samples of size n are drawn from any population with the population mean and standard deviation, then as n becomes large, the sampling distribution of sample means will approach normality, with population mean and standard deviation of that, you know, you got the population standard deviation symbol divided by the square root of the number. Okay, so basically what's being said here is sampling distribution of sample means will start to become normal in shape as sample size increases for any variable. So the bigger your sample, the larger your sample, the more normal it will start, the shape will start to become, okay? Even when the variable itself is not normally distributed across the population. So the idea is, as your sample size grows larger, okay, the sampling distribution of sample means will become normal in shape. And this is how, it's because of that, this is how we kind of start to get into that notion of, okay, well, we can't take the information from a population, okay? We can't we can't ask the whole population whatever question it is we're trying to ask, so we can ask a sample. But then it becomes, well, if we're getting information from a sample, how can we be sure that sample is going to give us the exact information we need? Well, that's what these two theorems kind of get at. Also, too, this is like thinking about this is why we have different formulas for populations and samples. You remember when I stated that the formula for population standard deviation differs from the formula for a sample standard deviation? I think that would have been back in chapter 3, if I remember correctly. Well, this is part of it, okay? This gives us a hint as to why. There's certain information that we must have when it comes to populations and when it comes to looking at things related to samples. But also when the sample is larger, the sampling distributions of the sample means get closer to normality. Okay, that's one of the key things to remember. So, but this theorem and the stuff that I'm talking about right now, it applies to larger samples. So for the sake of what we're doing with this book, a large sample will consist of anything equal to, or a sample equal to or greater than 100. You'll find some books in some professions will say 50, but for our purposes and anything that you do in this class, you need to use 100. So if sample is 100 or more, then it's a large sample. If it's less than 100, so if it's 99, if it's 98, it's a small sample. And you use whatever formula is there for a small sample. Okay, so basically what we have here, these are just some additional considerations, or additional things to think about when it comes to the sampling distribution. Because we are looking at it as a normal distribution and we're following some of those same parameters that go along with the normal distribution and the normal curve, we look at Appendix A, okay? So we look at Appendix A. Now we don't know the value of the population mean, but the mean of the sampling distribution is the same value as the population mean. That's one of the things to keep in mind and to remember when it comes to sampling distribution. And remember, it's not sample distribution, it's sampling distribution. And that's because you're taking multiple samples, all right? A sample distribution is just that sample. Now, the next thing, we do not know the value of the population standard deviation, but the standard deviation of the sampling distribution is equal to the population, or is equal to standard deviation divided by the square root, okay? Square root of the number, sorry. So these are things to just keep in mind and to consider. Now, what we have here, these are the different symbols and, the symbols and what they mean and different things like that for each distribution. So, and what it's basically, what we see is the shape. And when they say shape, they're talking about the shape of the distribution. That curve, that normal curve, that's what they're talking about right there. So for a sample and a population distribution, that shape can vary. We don't necessarily know what it is. It can vary. It might be skewed in one direction. It might look more like a normal curve. We don't know. It's going to vary. However, the sampling distribution, because of those two theorems, the first theorem and then the second one, the central limit theorem, because of those, we start to approximate or approach a normal curve and normal scores. Now, the central tendency for a sample is mean, but the symbol is different. So X bar, remember in some of the previous problems that we've worked on, we use X bar. So X bar, that's basically X with a bar over it. So X bar, that is the sample mean. But if you look all the way at the bottom and you see that funny looking M, well, that's mu. That's the population mean. So that's what that symbol means. And this is that time you're going to want to probably start writing down some of these symbols, or wherever it is that you keep information about symbols and formulas, you're going to want to start writing some of this down because it will get confusing and how you set up problems. Because as we start to move forward, you will see that there are going to be some instances where you need to use a formula for a sample and some instances where you need to use a formula for a population. All right, so dispersion is basically, the standard deviation. And so little s is the standard deviation for a sample. And I always forget what this symbol is. I think this is the little sigma, I think is what that sign is. But that is basically the sign for population standard deviation. And then you have the information that is there for the sampling distribution. For the sampling distribution, the mean for that is going to be the same as the population mean. And then the standard deviation is actually the population standard deviation divided by the square root of the number of your sample, of your population. Okay. All right. So that is one more slide. Actually, two more. I apologize. So what this is just some of that information again, but it's put in a different format. But it also has some of the symbols for proportions, which you will see on in the next chapter. So I would go ahead and write this down as well. Looking at the different symbols for each thing. So you have the symbol for the mean, you have the symbol for the standard deviation, and it's for each one of those different types of distribution. Now would be a good time to pause. That's why I'm not speaking. So I'll give it a few seconds for you to get a chance to stop and pause. Okay, hopefully you jotted this information down or marked it in your book or whatever you need to do, but moving on to the next and last slide for this particular part of the lecture. What this is right here, these are just some more points in terms of sampling distribution. Things that you need to know and remember when it comes to sampling distribution, the basic definition. I'm not going to read through all of these. I've said them multiple times, so you can take a moment and look through them yourself. But you know what it means, what the shape is. Also, when it comes to the central tendency and dispersion. So, knowing that the mean for a sampling distribution is the same as the population mean. Whereas the standard deviation of a sampling distribution, it's what we call standard error, is basically equal to the population standard deviation divided by the square root of n. And remember that capital N is typically the number of your population, or whatever information they've given you in the problem, okay? And the whole point and purpose of a sampling distribution with regard to inferential statistics, this is how we link the sample with the population. This is how we are able to say, we've got this information about this sample, and this is how we know what it's telling us about an overall population. All right, and on that note, this concludes the lecture for chapter 6. And so the next thing that I will move on to is the lecture for chapter 7. And that particular lecture will look at estimation procedures. And so some of this stuff that I've talked about in this particular chapter you'll see it again. And some of those concepts will start to come to play in chapter 7, estimation procedures.